you guys gotta let a man cook, all right? I saw the comments, I saw in the theory video I did, you're like, oh, where's the implementation? Where's the implementation? Well, here it is, here you go. 1 hour and 20 minutes of implementation. In this video, we are going to create libraries for our custom network protocol, and then we're going to take the existing program that I created in the previous video that I did on programming, and we're going to split it up into 2 different programs that talk to each other over a network. This is the Marvel Cinematic Universe of network programming, all right? If you look back through my channel, you see I taught you how to make a server, I taught you how to make a daemon, I taught you how to make a network protocol, like how to design it, and now we're actually going to bring it all together and create a networked application, okay? And this is not even the end, all right? We're going to do a very basic network program in this one, which is one server, one client. But then I'm going to teach you about threading. We're going to do multiple clients. We're going to do all sorts of fun stuff in upcoming videos. This is just let me cook, guys. Let me cook, all right? But without further ado, let's get into it. Here's some of the mining that I've done off camera, right? I've already gone ahead and implemented this protocol, and just like my last programming video, we're going to be recreating this from a blank file, basically. But the reason I'm showing this to you now is so you can get a high-level understanding of how I've actually put this protocol together. Now, if you think about our program that we're going to be splitting up into 2 parts, really the actual design of the protocol and the stuff that you define in these files is dependent on what those programs have to actually tell each other to do, if you get what I mean. So we split out our Rolexhound program. If you think about it, it did 2 things. It watched a file with iNotify for events, and then it sent the user a desktop notification depending on what event. So if we were to split this up into 2 programs, the most obvious way, and the way we're going to be doing in this video, is you have one program that watches a file with iNotify, and you have the other program that sends the user desktop notifications and they chat over the network. So if you think about what our stuff has to do now, this video, by the way, I did a video on protocol design, like a theory video. All of that stuff is prerequisite knowledge for this video, so if you haven't seen that one, I'll link it in the description. But essentially what we've got here is a 3-byte header, okay? So we've got an action, an option, a size, and our data payload format is an array of strings. So 3-byte header, and then an array of strings is our data payload. So if you come up here, you'll notice that I've done like some actions that I've defined here. Now an action is something that we're telling the other program to do. So I've got a watch action, which is pretty self-explanatory, you know, the user-facing program. So I'll tell you about this. Our iNotify program is still going to be called Rolexhound. Our user-facing program, which is the one that the user starts, the one that the user gets desktop notifications from, is going to be called Smartwatch. Okay, and the protocol is called NetFlex, okay, because we've got our watches, we're flexing on the net. It's called NetFlex protocol. So the user-facing application is going to have to tell Rolexhound what file the user wants to watch. And then we've got a quit, pretty self-explanatory. We've got notify. Now this is Rolexhound telling Smartwatch, hey, you've got to send a desktop notification to the user. We've got reply. Now my video on protocol designs, I went over message acknowledgement, validation, things like that. That's what this is. We've got status, which is events that can happen. So for example, we'll have a look at some of the options I've defined for all of these. So I've got for watch, I've got add and remove options. That's pretty standard. So you've got a watch and then you've got add or remove. For quit, I've got user or error. For notify, I've got all the different types of file events that we've decided we're going to watch. For reply, I've got all the validation stuff. So I've got, you know, valid, bad size, bad action, bad option, bad path, invalid data, etc. And it's also worth doing an unset for everything as well, because in C, when you've got your struct, you want to initialize it to something. And if you zero it out, you'll notice we've actually got valid data, that's zeros in here. So I just set this as, you know, unset, so that our program doesn't mistakenly think that, you know, a zeroed out struct is actually a valid message. Then for status, you know, you've got like success, you've got error initializing with iNotify, error adding to watch, error reading with iNotify. So you just have, like, when you're designing all of this stuff, you just think about what could go wrong with your program, what they're going to need to tell each other to do, and just the stuff that can happen. And down here, I've defined some other stuff as well. So like a minimum size, if you think about it, we've got a 3-byte header. So our minimum size is going to be 3. Our maximum size is 255 because our size parameter here is a uint8, which is max size 255. The question is, can you make this uint16 and up the size? The answer is yes, but we're not going to do it. And then I've defined the length of the arrays that we're going to get as data, right? So we've got, for watch, we've got one string in our data payload array, which is the file path to watch. Everything else is 0 except for notify, which takes 2. We're going to send the base path and the full path back to the program. So that's really it for the header file. You just define all of the actual hex values that you're going to use and what you want them all to represent, basically. If you come on over to the C file over here, this is where you provide like helper functions for your applications to use. So the most basic stuff you want to provide is like a serialize function, right? Where it takes this struct right here and puts it all into a buffer to be sent over the network. And you want the complement of that, which is the deserialize function, right? Which is taking a buffer that you've received over the network and converting it back to this struct here for your program to actually use in an easy, meaningful way. And you can provide other stuff too. So like you can see here, I've provided like factories because in C, you want to initialize all your struct values to something. So when I create a new struct for this, I can just call the factory on it and it'll initialize it to a bunch of stuff. And yeah, that's pretty much it. I've got a message reset as well. So like if we've allocated data here, it'll like free it just to reset the message so we can use it again without any dramas. The only thing I've given myself over here to start off with is all these hash defines because it would take forever to write those out in the video, right? But anyway, the first thing you're going to want to do basically is make your font size really, really small so that nobody can actually see it. Nah, I'm kidding. Listen, I do read the comments, all right? I read the comments. Font size is big and it's here to stay. The first thing you actually want to do is hash include standard in.h because when we're working with network stuff over the wire, we use uint8ts pretty much all the time. So we're going to want that. Now we're going to type def our actual custom stuff here. So uint8t flex act for flex action, and we're going to do another one for uint8t flex opt for flex option. That's just easier to keep track of, right? Now we're going to come down here and define our message struct, which is what our our application is actually going to use. So essentially, you just do struct flex message, right? And we're going to define flex act action right here, flex opt option. We've got a uint8t for the size, and our data is going to be an array of strings. And because we're going to be dynamically allocating this a lot of the time, we want to include a data length field as well, just so our program knows, the length of this array at all times. So come on over to this C function, C file over here real quick. And we're gonna do the standard things, so like standard lib, standard int, of course, uni standard, and of course, if it turns out we don't need this stuff, we'll go ahead and get rid of it later. And of course, we want libflex.h, which is our header file over here containing all of our protocol definitions. Now, the first thing we want to go ahead and do is make a serialize function. So it's easiest to start with serialize and deserialize. So we're going to start with a serialize function here. So start off by generating this one here, and it's going to take in at the start a uint8t buffer. I'm just going to call that buffer, and we're going to say that it needs to be at least the maximum size of our packet over here, which we've defined as 255. So we're going to have that. Okay. Now we're going to take in our message structure that that we are going to take from to serialize. So essentially, we're assuming that this is populated with the data that we want to serialize, right? Now the next thing I'm going to pass in, I'm actually going to go over here and define a new struct. And the reason for that is because when we come out of this serialize function, a lot of the time we actually want to return metadata about how the serialization went. And I'll show you what I mean when I define this over here. So we're going to have a serialize result struct, and it's going to have a size, and it's going to have a option called reply. So why have I done this? Oops, there should be flex opt, my bad. So why have I done this? Essentially, when we are serializing and deserializing, like deserialization, for instance, we want to return the size of the packet as well. It's kind of like you can kind of get it from here, but it's nice to include it all in one structure. So we've got all the metadata. We don't have to go going around the place. And this reply is going to be our validation result, right? So when we're serializing or deserializing, if we encounter an error while validating, we're going to set this so that our caller knows that there was an error when we were serializing. So we're going to also pass in this struct here, like that, and we can begin, essentially. So the first thing that we're going to go ahead and do is realize that we need to create a factory function. So when we pass this result in here, it could already be populated, so we want to reset it. So the first thing I'm going to go ahead and do is go void serialize result factory, which is going to take in a structure for our serialized results, and that's it. And we're just going to set default values for this struct. So result size is going to be -1 because we're uninitialized, and result reply is going to be flex. What have I set over here? Flex reply unset. So we're going to do that. So the first thing we want to do is make sure that our result thing is completely reset. So we'll just call serialize result factory on our result, which is all good. And so now we can go ahead and do some other things. So we're going to start off with some validation stuff. We want to validate that the action that we've been given is actually within this valid range. What I'm going to do now in this C file is define a couple of arrays, and I'll show you why. So we're going to start with a const unat. I can apply const here because these values are not going to change. And I'm going to call this option ranges, and it's going to be of size 5. What we're going to do in this array essentially is define the maximum option value for each action. Okay, so remember, options correspond to actions, and now what we're going to go ahead and do is define the maximum value of all of those options. And the only reason we can do this, right, is because we've got an ascending pattern here, essentially. If your values were kind of flip-flopping all over the place, you would need to use a different method, but we're going to do it like this because we can, basically. So for watch, our maximum one here is remove. So we'll do flex watch remove. And of course, if you were going to change these parameters, you'd have to update this as well. That's something to note. For quit, we've got flex quit error. For our notify, we've got flex notify move. For reply, flex reply invalid data. And for status, we've got flex status error read I notify. So this is going to help us down here when we go ahead and are validating this stuff. We can just check, if the option that we're given corresponds to whatever thing in the array. And again, we're using another trick here, which is that these are ascending from 0, so we can use those as the index of this array to sort of just cheat and not have to implement like a hash map or something like that. But again, if your format is different, then you would have to apply a different implementation here. We're just doing it because we can, basically. Yeah, so essentially the first thing we want to go ahead and do, if you notice, to do that, we've got to first make sure that the action we're given is within the size of this array. So what I'm going to do is define an integer called last action index. And essentially this is going to be size of option ranges, and I'll explain all this, so don't worry, divided by size of option ranges 0 minus 1. So what's going on here? We're taking the size of this option ranges array and we're dividing it by the size of the first thing and then taking away 1. So if you think of size of for this, because this is a uint8t buffer, it'll probably just be 5. But if we were to change this to like uint16t, then we can't just use like size of the array. We've got to divide it by the size of the first element in the array, and then minus 1 because it's an index, right? So this should come out to 4 as it is now. So the first thing we can do down here in our serialization function is check if message action less than or equal to last action index. So we know that it's, you know, inside of this array. And what we can go ahead and do is say buffer0 is equal to message action. So we're just setting the first thing here in this buffer to the message action. Okay, pretty simple. Now the next thing we want to go ahead and do is validate, like figure out how much data in the payload we have to add. So I'm going to define an integer up here, and it's going to be valid data length. Set that to -1 to initialize it. Now we're going to define another array, and the array is going to be called const int action sizes. And here we're just going to put in all of that stuff we defined over here, right? So flx dlen watch, flx dlen quit, flx dlen notify, and we're going to use the exact same strategy as before, which is where we're literally just going to index this array in order to figure out what the right value is. So we've done that. We come down here and we can just go ahead and say, I'll actually just give myself a bit more room here. We come down here and we can literally just go ahead and say that the valid data length is equal to the action sizes and then message action, because we just, you know, now we've got our valid data length. So we can do like an else statement right here. And what we're going to do is set the result. So if you remember, we defined a struct over here for the result of the serialization, and we can set that to flx reply bad action and return. So if you think about what this is going to do, So if you think about what this is going to do, we defined over here that if we get a bad action, this is going to be the response that we get. So this is 0x02. So what we've basically done here is just like the most basic validation, right? So we've checked that the action we've received is correct. And if it's not, then we put this in our metadata and return immediately. Because we're not going to bother trying to serialize the rest of the packet, because the person calling our function has given us something bad. Now, we can do the same thing here. So if valid data length does not equal message data length, then we can say result reply equals flx reply bad size, and then return. So if you think about what we do here, like we're just checking, so valid data length, we've got our data length up here, we grab that, and if it doesn't match what they've specified inside this message struct as the length of the data, like the number of strings in the array, then we're not going to bother serializing the rest of the packet. And we're going to do one more validation thing, and that's for the option. So if message option greater than, what did I call that one? Option ranges. I did call that option ranges. Yes. Option ranges for the action. Then we can say result reply is equal to flx reply bad option and return. So what we've done here is take this, the maximum option here, and validate that it's less than or equal to the option that the user has specified here. So we've done our validation of the header basically. So now we can go ahead and set buffer1 is equal to message option. So we set the option there. And now we're going to append our payload. So if you've noticed, I've missed one thing, and that is I haven't appended the size yet, because we don't know what the size is. We're going to, in this next section, we're going to add all of the data to the buffer, and then we're going to add the size that we calculate. So if you think about what we're going to want to do here, we're going to do a for loop until the length of the data, so the number of payloads in our array, and we've already validated that this is the same thing as the correct data length for this action. And what we can do here, the first thing I want to do is make sure that this is not null. So if data I equals null, we can do result reply equals flx reply invalid data, and return. So this is another validation thing, right? So if the user has specified a null, because remember this is a double pointer here. So if a pointer in this this section here is null, then that's invalid. We can't put that in our packet, so we're not going to bother. So now what we can do is loop through the string in that in the current payload. So for int j equals 0, j less than. Now, if you think about this, we don't actually know what the size of that string is. So you could use strlen here, but I don't really feel like introducing strings package, and I'm just going to use this as a demo to show you how to loop through this stuff. But essentially what we're going to do is j less than flx packet maximum size minus flx packet minimum size minus, and I'm going to have to go ahead and define a data size variable over here. Minus data size, and I'll explain all this, don't worry, j++. So what we're doing here, if you think about what this is saying, so data size is going to be our running size of data that we're going to set here. So if you think about what we're doing here, we're sort of calculating the maximum string length at this point in time. So our maximum size minus our minimum size, so our maximum minus minimum, because that's what we've got to work with, minus the size of the data that has already been put in the packet. And that's just for safety purposes, right? Make sure we're checking all our bounds. So I'm going to need another variable called running data size, which is going to keep track of the length of the current string that we're on. So we're looping through the string in this array here. So we're going to set running data size plus equal to 1. We're going to go ahead and set buffer flx packet minimum size plus data size plus j is equal to message data ij. So if you think about what this line here is doing, we set the buffer at the minimum size, so 3, plus the data size, plus j, which is our counter here. We set that equal to this value here. So now we're going to check if message data ij is equal to the null character, then we're going to break out of this loop because we've reached the end of our string. So remember, because this is a carstar start array, our carstar should be null terminated. So if we get to the end of this, then we can break out of this inner loop here and go back to the next string in our array. And then down here, we're going to do data size plus equal to running data size, and then reset running data size to 0. Now we can come down here and say buffer2 equals data size, because we've calculated the size of our payloads. And we can do result reply equals flx packet minimum size, sorry, meant to say result size, flx packet minimum size plus the data size that we've just calculated, and we can do result reply equals flx reply valid, and then return. So that's pretty much our serialization function, right? We validate all of the things that user has given us. We put them all into the buffer. So buffer 0 is message action, buffer 1 is message option. We append all the payloads, and then down here we've got our data size, essentially, that we calculated in this section here while we were appending it. So yeah, that's the serialization function. We'll move on to deserialization now. I can never say that. I can never actually say that. I just realized, by the way, that I should add a check here saying if valid data length not equal to 0 and message data equals null, we are going to set that as invalid data as well. Because some nerd in the comments is probably going to call me out for it if I don't. So there we go. The next thing we're going to make is deserialize function, which is pretty much the exact same thing but in reverse. So we'll start off by saying deserialize, and we're going to say, like, it's going to have the exact same parameters, right? So we're going to have a buffer with our maximum size here. We're going to have our message, and we're going to have our serialization result right here. So we're essentially going to kind of do the same validation techniques as the first one, but in reverse. We're going to do it on the buffer instead of on the struct. So we can go ahead and do that now. So if buffer 0, remember this is going to be our action, is less than or equal to last action index, then we can say message action. Actually, the first thing I want to go ahead and do here is reset that message. So to do that, we are going to need some kind of reset function. Now we already have defined up here a result factory for this, but we can define a factory for, so void flex message factory, and it's going to take in our message. So message, and we're basically just going to set message action equals, and this is where this stuff over here comes in handy, like the unset stuff we were doing. So flex action unset message option is equal to flex. I should have an unset option somewhere here. Flex unset unset. that works. Unset unset. What else do we have down here? Our size, we can set that to like 0. We can set our message data to null, and we can set our message data len to 0. So that's our factory. Now, if you are paying attention, you might have noticed that since this is a double pointer, we could potentially have allocated data here. So what I'm actually going to go ahead and do is create a function to handle that as well. So I'm going to make a function called flex message reset. And it's essentially going to be kind of a wrapper for this function, except it's going to free this data as well if that's applicable. So essentially we're going to do struct flex message message, just like the first thing we did. And then we're going to say if message data does not equal to null, so this should be MSG, is not equal to null, then we can, if it's equal to null, my bad, because we want to make sure that we just do the easy stuff first, we can literally just call message factory on the message and then return, and that gets this out of the way. So like if this is null, we don't have anything to free, so we can just call the factory on it and get that out of the way. But if not, then we're going to loop through. We're going to loop through the entirety of the data and free it all, right? So if message data, I don't know why it's adding C++ stuff there. If message data I does not equal to null, then we can go ahead and free it. Because it's important to note, like in my last video, I got some nerds in the comments saying like, oh, you didn't free that memory, you didn't free that memory. The kernel will do that for you when the program is killed. We only allocated that once, so you didn't actually have to free that because the kernel will just do it. But in this case, like, we are going to be continuously allocating this data, so you do have to free this stuff. So we're going to free it here if it's not equal to null. And then what we're going to do is free the message data pointer, because remember we have to allocate the car star star as well. And then we're going to call flex message factory on our message. So yeah, we just like wrap this function and that'll unset everything for us after we free the memory that we need to free. So that's our message reset. So the first thing we're going to go ahead and do up here in our deserialize function is make sure we start with a blank slate. So serialize factory on our result, because remember we want to clear our result first. Then we're going to reset our message. So flex message reset on our message. And now we can actually start doing our validation stuff. So if our action is valid, then we can set the struct value to the first buffer index, and we can set valid data length, which I'm going to have to define up here again. You'll notice we'll be defining a lot of the same parameters as our serialization function because we're literally just doing that in reverse, right? So valid data length is equal to action sizes message action. That is what I called that, isn't it? Yep. So like that. Else, again, same thing as before. Result reply is going to be equal to flx reply bad action, and we return. because otherwise the sender has sent us, an action that's outside of our range, so we can't go ahead and do that. Now then, we can validate the option. Again, literally the same thing as the serialize, but in reverse. So if buffer1, which is our new option, greater than option ranges, I don't know why it keeps wanting to remove that space there, but anyway, message action, which we can do because we now set that. Then result reply equals flx reply bad option and return. So in this case, we got a bad option that we don't care about, so we return. Otherwise, we can, of course, go ahead and set message option equals buffer1. So we set our option here now that we know that it's correct. So the next thing we want to go ahead and do is validate the data. So if valid data length, which we got just before from this section up here, which remember is from this array up here, if valid data length is equal to 0, in that case, we don't really have to do much else. Like the rest of this deserialization function is going to be taking our data and putting it into the struct, which is going to be a whole bunch of operations. So we don't want to bother even thinking about that if our data length is 0, right? So now we just check if buffer2, which is the size parameter, does not equal to 0. So that's in the case that the sender has sent us data that we don't, like, given our protocol definition, is not valid. So if that's not valid, then we can just say reply equals flx reply bad size and return. Actually, I'm going to get rid of this because we're going to have an else statement as well. But essentially, else result reply equals flx reply valid. And the reason, and then we're going to return after that. So the reason for that is because, if the size that the sender has given us is not equal to 0, but our valid data length for that action is 0, that's invalid. We don't want to handle that. But otherwise, it's a completely valid thing, right? And because this is 0, we're not going to be handling our data extraction, so we don't care. We can just set it there and return. So now, we can go ahead and set message size equal to buffer2. And the reason we don't have to do that here, by the way, is because that's already set for us in our factory. So it'll just be 0 by the nature of things, so we don't have to set it before this if statement. And what I'm going to go ahead and do is declare a new variable, and I'm going to call it data sizes. So it's going to be an int star data sizes, and I'm going to initialize that to null. So the reason I'm doing this is because now what we're going to have to do is allocate space for this data here. And the way that I'm going to go ahead and do that is pre-calculate the size. And there's going to be like a nerd in the comments who's like, oh, you could do it this a better way. This is an example video. The way that I'm going to do it now, we're going to pre-calculate the size and then allocate based off that, because from my intuition, I think that's faster than reallocating on every character. So we're just going to do that. It's pretty simple to follow, pretty simple to understand. So data sizes, which are going to hold our pre-calculated sizes, we're going to malloc enough space for it, so size of int times our valid data length, because that's how many data that we're going to need to get from the packet. And we're going to loop through the entirety of the packet. So int I equals flx packet minimum size. So we're starting on the like the 3 index, because if you think 0, 1, 2, that's our header, 3 is the start of our data, and minimum packet size over here is declares 3. So we're going to loop through that. I less than flx packet maximum size, because we don't want to overflow, I++. And what we're going to go ahead and do here is a couple of things. So the first thing that I'm thinking is our stuff is null terminated. So if buffer I is equal to the null character, then data sizes. Now we come to this section here. We need something to keep track of which data size we're actually on. So I'm going to add another variable up here, and I'm going to call it int data size equals 0. This is the same variable name as the one in our serialize function, but they're different. Actually, I might rename that then to like data size index. That's probably better. So data sizes, data size index equals ++ data size. and I'm going to need another int up here called data size, which is going to be the size of the current. So the variables we've declared here, data size is going to be the size of the current string that we're examining, and data size index is the current index of our data sizes array that we're using to store these calculated sizes, right? So that's all those variables there mean. But basically, you know, our data size is added to include the, like I'm doing ++ here because we got to include the null character as well. But then what we're going to do is put our data index ++, and we're going to reset data size to 0. And then I'm going to continue. So what we're doing here basically is like when we've reached the end of our string, we allocate space for the null character, add that to our data size at the correct index for that character, that string in our data payload. Then we increase the size of our data size index, so we're going to the next one, and then data size equals 0, continue. Now, if you are switched on, you might realize that, well, if they send us more null characters than necessary, we could actually overflow this data sizes thing here because we only allocate for valid data, right? So, and you're right, we're gonna have to catch ourselves there and check that. So, if data size index is equal to valid data length, so we've reached the, like we're like going to overflow basically, then what we're going to go ahead and do is say break. So essentially we're at this point here. Like if we're still looping through the packet, but we're about to overflow if we index data size index now, which is what happens when it's equal to the size that we allocated, because remember the index is one less, then we're going to break because we've reached the end of our valid data, so we don't actually care. The only next thing that I'm going to check here is if data size is equal to 1, then what we're going to do is free data sizes and put a reply for bad size, because if you think about what would be the case here, essentially it's just a null character. Actually, I don't think that would ever be hit, but I've got it in my the stuff that I did before the video, so I'm just going to leave it in, and I might just put like some text on screen whether or not this is actually needed or not, because I think based on the control flow of my program, now that I'm looking at it, this section here might not actually be necessary. But anyway, I'll leave it in for now and I'll check it later. So the next thing that we're going to go ahead and do down here is validate that the stuff that we've received is actually a string. So if you remember, when we're working with networks, we can get a uint8t buffer, right? And the ASCII character range is limited. So the actual the car data type here is ASCII. So if our thing is outside the ASCII range, it's not valid. So we're going to check that. So I'm going to go if buffer I is greater than the exclamation mark, because if you get up an ASCII chart, I'll flash one up on screen. I've actually got an ASCII chart above my computer right there, so I can just look at it. But exclamation point is the greatest character in the ASCII character set. So if it's greater than that, or, sorry, smallest, my bad. The greatest character is the tilde. So if buffer I is less than the exclamation point or greater than the tilde, that's invalid. So we don't want to handle that. So we're going to free data sizes because, again, you know, we've got to free the memory we've allocated here, because this is going to be a function that's called multiple times. We're going to set the reply to invalid data, and we return here. Now, if we've made it this far, then what we can do is add 1 to data size, like that. I'm just going to do one more check here, and that is for if the I is greater than message size, then plus FLX packet minimum size, because we're starting from there, that's our offset. Then essentially what we're doing is checking, hey, the size that you told us, is that actually the size that you gave us, right? So if this is the case, then we're going to free data sizes, because we have to do that every time we return now. We're going to give them a FLX reply bad size and return here. So that's essentially our payload function. And now if we go down here, we've calculated the sizes of our of our data. So we can go ahead and just set msg data is equal to car star star malloc size of car star times valid data length. So we're allocating space for our payloads now in our struct. We can set the data length is equal to the valid data length. So that's how many are in that array. And what we can do is go for int I0, I less than valid data length, I++. Now we can say msg data I is equal to car star malloc size of car times data sizes, which is the I. So we're using the value that we just calculated up here for data size here. And the reason I did this pre-calculation is because we can also do validation in that as well. We can kill two birds with one stone basically. So here we can use that data size that we've done to allocate space, like the correct amount of space for our character here. And if you remember, we included the null character in our space allocation as well, so we don't have to add a +1 here either. So now what we can do is copy over the actual data. So int j equals 0, j less than the size of our data. I don't know why it keeps removing the spring there when I autocomplete, but oops, I, and then of course j++. What we can just do is msg data I j is equal to buffer j plus, and we're going to need a data offset. So the data offset variable, I'm going to initialize that to the minimum size. And the reason why we need this offset here is because the buffer, right? Our j is starting from 0, and our data offset, like we're getting stuff from the buffer explicitly. So we want to, like, the packet size is 3, the header size is 3. So our data starts after the 3. So we're going to have a data offset. And the reason I'm making it a variable is because it's actually going to increase. It's going to increase as we keep going, right? So basically, every time we add stuff here, we're going to have to do data offset plus equals to data sizes I. So that when we get the next thing from the buffer, we go from, like, you know, we start at after the header, and then we start after the last payload. So now that we've done that, we could go result reply equals flx reply valid, because we've done all our validation, we've copied over all the data. At this point, we're good, right? Result size is equal to flx packet minimum size plus message size. So we just set the size for our metadata. We remember to free our data sizes, and we return. And that's deserialization. So essentially what we've done is take the opposite of serialization. So we've gone from a buffer to this struct, and it's a bit more involved, as you can see, because we've got to actually validate our data. We've got to do some dynamic memory allocation. We've got to do all kinds of different stuff. So yeah, that's pretty much it for deserialization. So now what I've done is I've just added a debug thing here called print packet. I'm not going to write it out because it's pretty obvious what it does. You are literally just printing out all the struct members. And then in our header file, I've also added function prototypes so that applications can use it. This is all pretty standard C stuff. I don't need to do it live. And then another thing I'm not going to bother doing live, I've made up this program called flextest. And what it does is stupidly simple. I've just defined a packet here that I'm going to try and deserialize, and then I'm going to reserialize it, and we're going to see what happens. So you can have a look at the buffer here. I've got action notify, watch, remove, and if you remember, notify takes 2 payloads. So I've literally just done hello, and then xoxo is the length of this, which is 12, I think. And then I've got 2 more strings here that I'm going to change it to, and then we're going to serialize that and see what happens. So if I just go over here and make that, I've already made it, I guess, and then just do flex test, you can see here that our packet is printed out. So the command, we first try to deserialize this right here. So we deserialize, the command is 2, the type is 1, that's all correct. The size is 0xc, the data is 0 is hello, the data 1 is hello, and then it prints out the serialization of the packet, like we reserialize it here, as you can see, and then we just print out the data. So deserialization looks good, serialization looks good, then I mess around with the data a little bit and I try and serialize that, and as you can see, we've got a much more complex thing here that's been done. And I've already pre-checked, like before the video, because I rewrote it before the video, of course, that everything's working good. But this is just, you know, flex test. We're just testing. So it looks like our library functions are working well, so we can actually put this into an application now. This is where the fun actually begins, my friends. We're going to take this houndog.c file over here, which is the original Rolexhound program that we wrote in the video. That if you haven't seen it, if you want to see me write this program, I'll link it in the description. But we're going to take this program and make it into a networked application. So the first thing that I'm going to go ahead and do is copy it all over over here like this, right? And just give me a second here so that my LSP server can actually complain about things. And we're going to strip out all of the libnotify stuff. Because if you think about our architecture, this program here is the Rolexhound is just going to watch file events, and then it's going to send that over the network, and our user-facing application Smartwatch is going to handle the desktop notifications. So I'm going to start stripping out all of the libnotify stuff. We'll just get rid of it all because it's unneeded and unnecessary. So get rid of this, get rid of this. We don't need this anymore. We don't need this anymore. Isn't it great just removing stuff? Don't worry, by the end of this program is going to be way longer. Way longer in terms of lines than it was before we got rid of all this stuff. So we're going to get rid of this stuff as well, because that's not needed. And so now we're left with a program that basically all it does is the iNotify stuff, which is what we want. So the first thing we're going to go ahead and do is add in all of the network headers that we need. So the first one I'm going to include is net-inet, and I'll show you what they all do as we go through and actually add the network code. And then we're also going to need sys/socket.h, and I think that's it actually. Yeah, we should be good there. So now if we go down to main, we're going to have to define a couple more things here. So, oh, and also, my bad, I forgot. We are also going to need libflex.h, naturally, right? Naturally. So now what we're going to do is define some extra things here. Now the first couple things that we're going to go ahead and define are our structs for our messages. So flex message, we're going to need a read message and a send message. We are going to need a serialization result. And now we're going to need to define our network stuff. So network stuff, the things that we need a couple of file descriptors. So we need a socket file descriptor. We need a client connection file descriptor. Set those to -1. And we need a sock address for the server address. And we need one for the client address as well. Now this is the stuff that we're going to pass to the system calls to actually do network stuff, basically. So we're going to do the network setup in these structures, and then we're actually going to send that off to the system call, which is going to do all the kernel level stuff for us. So I'm also going to do a bytes read equals -1, because when we do read calls, we're going to need to know how many bytes we're actually reading. So now I'm going to actually get rid of argv, and the reason I'm going to get rid of our argv handling is because we're going to do that on the user application side and not on this remote application side. So we don't actually need argv, because remember, in our protocol we had defined that the user is actually going to tell us over the network which file it wants us to watch. So get out of there. Get out of my get ignore. That's useless stuff. So we're actually going to tell over the network which file we want to watch. So now what we're going to go ahead and do is oops, the argv stuff there. Yeah, we'll fix that when we actually get the stuff over the network. So ignore that for now. But now what we're going to go ahead and do is actually start setting up our network stuff. So we are going to do if socket fd is equal to socket AF inet, so we're doing an internet one instead of like a Unix socket or something, sock stream, and then 0. So basically we're selecting an internet socket, so TCP, UDP. We're doing a stream-based socket, which is pretty much going to be TCP, and then this one here is like a protocol specifier, and 0 is like automatic, so it should select TCP for us, but it doesn't matter because we're going to be reading it like a stream anyway. But under the hood, it should be TCP. So then we're going to check if that is equal to -1, which is the error code for the socket function call. And you can check here, right there, or on the manual page for this system call, it says -1 for errors. So we're going to check if it's -1. And we're going to fprintf to standard error creating socket. And we're going to exit with a new exit code. So if you remember from our first video, we were defining a whole bunch of exit codes up here. I'm just going to be really lazy and just like add another one on here. And the source code that I post, I'll have cleaned all this up, so don't worry. But we're just going to exit with a new one for the socket stuff. So ext error socket, and we exit like that. So now we're going to zero out the server address because we're going to actually go ahead and start doing stuff with it. Like this. And now we're going to set the server address family to inet because we want to use an internet one. Now you could do Unix sockets as well. I'm going to do TCP in this video, or like inet, because it's much more common, but I'll do another video maybe where I cover Unix sockets as well. And now I'm going to do server address.sin adder.sadder equals htunnel in adder any. Basically what this means is that we're not going to specify an explicit address for this because we're the host basically, so we don't really care. Any address here is fine, but when we do this on the client side, we are going to have to specify something here. So now we're going to do server address.sin port, and this is where we've got to specify something else. So up here, I'm just going to hash define the port as 5521. So we're going to listen on port 5521 for our client. So here we're just going to do port. And yeah, sweet. So now we've set this up, we can start actually, creating the connections. So if bind socket fd, and then we want to do struct sock adder cast of the server address, size of the server address is -1. So what does this do here? So bind basically is where we're asking, hey, can we get this address here, like with these parameters, so port 5521 on any address, can we get this actually allocated to ourselves? And in some cases, the operating system will say no, somebody else is already using it, or if you don't clean up correctly in time, then sometimes it won't let you reuse it. So we're going to say if fprintf standard error binding to socket. And we're going to exit with ext error bind, and I'm going to go ahead and define that up here. So ext error bind as 8, come back down here. So if we've made it this far, we know that we've created the socket successfully and we've bound to it. So now we're going to listen for connections. So if listen on the socket fd, and then I'm going to say one connection we want to buffer before allowing, refusing more. That's what this parameter is here. In another video, I'm going to go over more advanced socket programming where we're actually going to handle multiple clients, do some threading, throw all that jazz in there. It's going to be pretty sweet, but for now we're going to do something real simple. We're just going to have one, okay? So if listen here, and we're just going to check what the return value of that is, return -1 for errors. So if listen equals -1, fprintf to standard error listening. Always remember my new lines. ext error listen. And again, we're defining exit code. Somebody asked in the comments, by the way, if you could use an enum here. The answer is absolutely you could. You could absolutely use an enum, but I'm doing hash defines. It's all like personal preference. There's so many ways to do the exact same thing. But yeah, you could use an enum here if you wanted to. So error listening, and now that we're here, we can say Rolexhound is listening on this port. Because if we're here, we know that we've set up our socket correctly and we're listening, and that's all good. There's no dramas. So now we're actually going to accept a connection on that socket. So we can go if connection fd is equal to accept from the socket fd struct sockadder, cast that to the client address this time, because remember we're accepting a connection, and then we've got to specify the address size, which I haven't actually defined, so let me go ahead and define that. So up here we are going to need a socklenT address size, which is just the size of the sockadder instruct. Where am I? Here I am. So we go ahead and do that, and then we're going to check if that is -1, because that's the error return code for that as well. And now, you guessed it, if it's -1, error accepting connection. And we're going to exit with another exit code. Exit error con is pretty simple. Hash define ext error con as 10. No dramas, no dramas. Oh yeah, I forgot to specify to stamped error. I do that all the time. Like I treat fprintf like printf all the time. It's annoying. So now I can go ahead and set up our structs for our application level protocol. So I'm going to go ahead and say read message is equal to struct flex message malloc size of struct flex message, and we're just allocating our pointers here. Send message, I'm going to do the exact same thing. So allocate that, and now it's important to note that we aren't going to bother freeing this because these structs here are going to be allocated at the start of the program and not reallocated until the end of the program, so we don't really need to bother. And then we're going to do the same thing with our result. So result equals struct serialize results malloc size of struct serialize result. And now what we're going to do is use our factories that we made. So serialize result factory on result. Make sure we're just initializing all of these, and we can do flex message factory on our read message and our send message as well. There we go. Cool. So now technically we've set everything up to be able to talk to other applications using our protocol. So now what we're going to actually go ahead and do is start a like a while true loop basically, where we're going to sort of try and negotiate the init sequence for this. So in this video, essentially the network comps are going to be very basic because this video is also like really long at this point, and we're going to do more advanced stuff in another one. But basically what we're going to do is have it so that the initialization negotiation is going to be where the user-facing program, so Smartwatch, sends a watch command to Rolexhound, and then after that, Rolexhound is just going to send it update events. So there's two-way communication, and then there's just one-way communication. So to negotiate this initialization thing, we're going to do while true, bytes read is equal to read from our connection file descriptor into a socket buffer, which we are going to have to go ahead and define up here. So this is our iNotify buffer. We're going to leave that as is. And I'm going to make a uint8t socket buffer, which is flx packet maximum size. So that is going to be our buffer we're going to read into. And now we're going to basically just do size of socket buffer like that. So we're reading, it should be the maximum size. So now we're just going to check if bytes read equals 0. That is the error condition for this read function. So if like 0 for end of file, and check this here as well as -1, we're going to say error reading from socket. Can't spell error apparently. Error reading from socket. Keep it real in these videos. And again, like I mentioned before, I forget to specify standard error. Now we're going to exit with ext error socket read, which I will hash define up here. ext error socket read as 11. So now we've essentially read something from the socket, right? So what we're going to do is deserialize that. So we've got our socket buffer, we've got our read message, oops, read message, and we've got our result that we can pass in here. Now, if you remember, our deserialize function does the validation for us. So we can just go ahead and check the condition of here. If result reply is not equal to FLX reply valid. So if we get an invalid message, what we're going to do is print to standard error, received error, this from client. And we can just put in result reply. So we're just letting us know what the actual error code was. Now we're going to send them something back. So send message action equals FLX action reply. Send message option is equal to result reply. So we already know what we're going to reply with. And the size, of course, is going to be 0 because we don't have any data payloads when we're replying to things. So now we can zero out the socket buffer because that's what we're going to serialize into. FLX packet maximum size because that's the size of our buffer. And we can serialize this, just serialize, into socket buffer from send message, and we input our result. And I'm not going to bother checking the result because you and I know that this is going to be correct. There are cases where you can just ignore it. You got to give yourself some credit, right? Like I know this isn't going to error, so I can just go ahead and not check it. And then I'm going to write that to our connection file descriptor. So write that there, and then size of socket buffer, just like that. And of course we are going to continue. So essentially if we receive something bad from the client, we're going to send them a reply telling them why it was invalid, and we're going to continue our loop and try and get another message from them. So now we can check if read message action does not equal to FLX act watch. So if you think about it, like theoretically they could send us something valid, but it's not the watch command. And in that case, we want to ignore it. And if all of that is satisfied, we can break. So essentially what that means is we are reading from our client until they send us a valid watch request. And then after that, we break. So now theoretically in our read message, we have a valid thing, right? So what we can go ahead and do is set up like essentially from our hound dog over here. We're going to do pretty much the same thing. So we're going to grab this base path. Like actually I'll allocate watch path as car star malloc size of car times strlen, and we can use strlen safely here because our deserialize function validated that it was a valid C string. Read message data 0 plus 1, and I'm going to have to define watch path as a car star up here. So now we can just do strcpy, and again, like we validated everything so we can use it. I don't want to see any comments about it being unsafe this time because you got to trust yourself, all right? You got to trust yourself. You got to do your checks, and you can do it if you trust yourself. Now we are going to take this like base path stuff down here, and we're going to move it. We're going to move it up, basically. So we're going to move it up here. And instead of mallocing this, I'm just going to set base path is equal to watch path. And then we don't need to do this anymore, so we can get rid of that. And I need to define a pointer for token. So we're pretty much doing the, oh, I've already done that, my bad. So we're pretty much doing the same thing as what we were doing originally. So why are you complaining? Oh, forgot my semicolon. Happens to the best of us. So yeah, basically we're just doing the same thing, but this time we're getting it from the network socket instead. And then we're doing the same thing. We're initializing with iNotify. We're getting the file descriptor. I can uncomment this now because it won't complain. And we can move this and change this to a watch path. So that'll add it to the watch path. And basically, yeah, we're just getting our path over the network now. So theoretically, we should be able to move over here. Now this while true loop here, if you remember, is our iEvent queue read loop. Now, if you think about what we're going to have to do here is essentially down the bottom, instead of sending the user a notification message, we are going to send them a message with our protocol over the network with an action saying notify. So the first thing that I want to go ahead and do here is at the top, well, every time we get one of these iNotify events, what we're going to do is, I'm actually going to get rid of this notification message because we're going to set that on the actual smartwatch side instead. So I'm going to get rid of all of these here, and we're going to replace them with something else. If you remember from when we were designing our protocol, we actually specified options for all of these different events, like here. We're just going to change that. So I don't know why it keeps doing that, but we're going to do send message option is equal to FLX notify create, right? So we're just going to go ahead and swap all of those over to setting our send message option to this. I'm going to cut here and do it because it's going to take forever. So I've done that. You can see here, depending on the mask, we're just going to set a different option, which was specified over here. Now, every time that we get an iNotify event, we want to send a new message. So if you think about what we're actually going to have to do, we want to sort of clear our previous send message to make sure there's no data there. Now, we could use, so there's two options we could use. We could use message factory or message reset. I'm going to choose factory for this video, and I'll explain why in just a second. Because our actual, if you remember from before, our reset one will actually attempt to free the data here, which is not actually what we want in this scenario, because our data is actually stuff that we want to keep running while the program is operating. The reason why we made that reset with the free earlier is because when we actually get this talking to multiple clients, we're going to want to do that where you can add and remove stuff. We're going to want to free the data as well. We're going to store it in a less permanent way than here. But for now, we're just going to use the factory, and we're going to free the data manually later. So down here, after that, you can just set up your send message. So now that we've got a notification that we want to send, action equals FLX act notify, right? Send message option, oh, we've already set the option, so data length is equal to FLXDLen notify. Send message data, and here we're actually going to malloc, so car star star malloc size of car star times FLXDLen notify. So we're allocating enough space. Oh, speaking of allocating space, I'll allocate some space for me here. We allocate enough stuff for our notify thing here. So now what we're going to do is set send message data 0, and this is why we don't want to use our reset function to base path, send message data 1 to watch path, because this is stuff we want to keep in memory permanently until our program's killed. If we use reset, it'll try and free this, and we're going to have a bad time. So now we're going to B0 our socket buffer, get it ready to serialize our stuff into it, so just set it to 0. Now we serialize. Again, if I will autocomplete to the right one, that would be great. So serialize into socket buffer from our send message and with our result. And now here we actually do want to check result, because this could this is variable, right? Like as we're adding and removing stuff from the watch list, it could potentially get too big or something like that. So we are actually just going to go ahead and check the thing here. So FLX reply valid, fprintf to standard error, %x constructing watch notification, and we give it the result reply here. So we actually know what we're dealing with. And this time I'm actually going to just go ahead and continue. So we'll try again. We won't exit, we'll just continue. Now then, if this is the case, we can say sending a notification to Smartwatch, because that's our client over the network, and we can write to connection FD our socket buffer with the size of the socket buffer, like that. Now what we're going to do is free send message data. Now, there's an important distinction to make here between freeing this car star star here and freeing the the values that are inside it, right? We don't want to free the values that are inside it, but we do want to free this allocation here, okay? So we're just going to go ahead and do that down at the bottom. So now theoretically, Rolexhound is pretty much ready to go. To create Smartwatch, we're going to do the exact same thing to start off with, which is copy in our original Rolexhound definition here. now we're going to get rid of a couple things like all the iNotify stuff. So yeah, if you remember, like all we've got to do here basically is notify uninit, because we're not handling that here anymore. Like we don't actually care. So we can get rid of all of the iNotify stuff, which is brilliant. iNotify is here, so we'll get rid of that. iEvent descriptor is here, we'll get rid of that. How good, how good. And this base path stuff is handled in Rolexhound now, so we can get rid of that. Get rid of these. How good, get rid of that. And now this main loop here is going to be changed significantly. So what we're going to do is get rid of all of this, and like we actually don't need this inner loop at all. I think we can just get rid of this inner loop, bring this all back in indent, because this while true loop is just going to become a loop for reading from the network socket. So we can get rid of all that. And now what we're going to do is include our networking stuff again as well. So the ones that we need for this are a bit less than the other ones. So include ARPA/inet, and we need sys/socket, and that's it for the hash includes for this section. So now we come back down to main, and we can do a little bit less on the client than we do on the server. So we're going to need a struct sock_adder in for the server address. We're going to need still going to need like flex message structs for read and send. And we're still going to need a serialized result for our serialization functions and things like that. Now, what we're going to go ahead and do here with the argv handling is essentially, I'm going to add 1 to this, so 3. And what we're going to do is change this to host and then path. So what we're going to do is on the user side, you can specify the host that you want to try and connect to that's serving you our new Rolexhound program that's listening for connections. So down here, what we're going to go ahead and do after we initialize with libnotify, we're going to say socket fd, which I actually need to define. So we still need a file descriptor for our socket. Our socket file descriptor is going to be equal to socket af inet sock stream, so the same parameters as our server, 0. So now we're going to set server address.sin family is af inet. You'll notice we're doing a lot of the same thing here as we did on the server side, but we're going to have to do less of it. And now this is where it's going to change. So on the server, you remember we used the special any address. In this case, we're actually going to do inet address argv1, because that's the host that we want to connect to, basically. So now we can do server address.sin port equals htons port. And of course, we need to hash define that up here. So hash define port 5521. So now we can go ahead and try and connect. So if connect socket fd struct sock_adder of our server address, size of server address equals -1. That's our error condition. And oops, I need to do that. Then we're going to printf to standard error with saying error connecting to Rolexhound with parameters %s, %d, new line, and we're going to specify our host here that we tried to connect to and the port that we tried to connect to. And now we're going to exit with an exit code that says exit error connection, basically. So we can go up here and define that. Exit error connection as 7. So come back down here. Now we have a connection, so we're good. And we're going to do the exact same thing as Rolexhound here, where we set up our stuff here. So I'm just literally going to copy and paste that. So just setting up our stuff here. Oops, and of course, I forget to hash include libflex.h. Classic. But here we go. So now we are ready to rock and roll with that. And what I'm going to do is our initialization handshake, by the way, remember it starts with us sending a add watch action. So act watch, the option is going to be FLX watch add. And we are going to skip the size for now because we're going to calculate it later. But data length is equal to FLX DLAN watch, should be 1. And then our data, we are going to malloc size of car star times FLX DLAN watch, which should be 1 again. And now we can say send message data 0 is equal to argv2. Because that's, if you remember, like up here, we've specified that's the part that we want to be watching with Rolexhound. So now what we can do is serialize, and serialize will calculate the size for us and apply it, so we shouldn't need to bother setting it. So socket buffer, which again I need to go ahead and define, so int8t socket buffer FLX packet maximum size, come back down, and we are going to say send message and our result. And this time we are going to check it because remember we're handling user input. So if we're handling user input, we need to make sure that our serialization function works correctly, because they could put in a path greater than our maximum packet size and that would mess with us a little bit. So flex reply valid, fprintf to standard error, error send x constructing init packet. You get the idea by now. Set that to 8. So here we are. Now all we need to do is write to socket file descriptor, our socket buffer, size of the socket buffer, and yeah, our init packet should be away. So at this point, what we can do is free send message data, because we're not going to be sending any more messages to our guy, right? Like we're done. And we can reset our send message. The only message that we're going to send from now on is like an invalid, right? So up here in this while true loop, the first thing we're going to do, we can get rid of all this junk. And I'm actually going to get rid of these from up here because it's not needed. We're going to modify this and change it to a network socket call. So bytes read, which I'm also going to have to define apparently, because I forget to do that all the time. So bytes read is going to be equal to our socket call. So we're going to read from our socket file descriptor into socket buffer, size of socket buffer, and now we're going to check if the bytes read equals 0 or bytes read equals -1. Because remember, the client can, like the server, can close the connection as well. And we're going to say error reading from socket to standard error. Again, I've forgotten it. It's a pretty common theme. And here we're actually going to exit the program. So ext error socket read. That'll do. Grab that, come up here, just define as 9. So here we are. And now what we can do is deserialize our buffer into read message with our result. And we're going to go ahead and check if result reply. You'll notice that pretty much most of this stuff, like most of the actual code that we write, a lot of it is like error handling, because when you deal with network sockets, there's a whole lot of error handling that actually goes into it, right? Because theoretically, you could get sent anything over the network, and your programs need to be built in such a way that you're able to handle that without it going down. Like if you've got a bad actor, on your network trying to send you stuff and crash your daemons and stuff, you're gonna have a bad time if you can't handle these errors correctly. So a lot of the handling that you do, a lot of the like handling that you do with network stuff is pretty much all, you know, it's like all error handling pretty much. We're going to zero out our socket buffer and get it ready for us to serialize into size of socket buffer. Oops, I don't know why I included that there, but that's what we want to do. So we B0 that out, and now we are going to serialize. And remember, this time we're not going to bother checking because we trust ourselves. So socket buffer, send message, and then result. Now we can write this to our socket FD. Socket buffer, size of socket buffer. So now we've basically just sent our connection partner, hey, you sent us something bad. Can you fix that up for us, please, boss? And if they're nice, they'll send us something back. They'll send us something nice back. And now we're just going to reset send message like this. And we can continue the loop. So now the next thing I'm going to do is say if read message action is not FLX act notify. Now, because remember, we could pass that validation check and they could be sending us something different than what we're expecting. So we're just going to continue if it's not a notification. And now, literally what I'm going to go ahead and do is a big old switch statement, which I'm not going to do live. I'll just paste it in. Because as you can see, that would have taken me forever to write out on this video, and it's already too long. But essentially, yeah, here's where we're at. Now we can just get rid of this iNotify stuff down here and change this to read message data 0, which is going to be the base path, and then the notification message here, which is we've selected based on the option that we've got from our read message this time. So we're changing the message based on the notification. And that should be it for Smartwatch. So we'll just head on over and we'll test these bad boys out. Here is where we get nervous because we're over here and we're going to test the programs that we just created live. So what we're going to do, we're going to go ahead and start Rolexhound up. And as you can see, he starts listening on port 5521. Now we're going to start Smartwatch with the local host for now and rolexhound.c. So now you can see that we've gotten to this stage where Rolexhound initialized and he's waiting for the I event. So now if I go ahead and edit rolexhound.c, boom, check that out. Up here we got a notification. So Rolexhound sent some notifications to Smartwatch. Now you might have noticed that he sent multiple. libnotify has a thing where it's like if you send too many notifications too quick, you might not get it. So that's why, you know, he sent a couple to Smartwatch, but we didn't get them up there. But if I go ahead and just add a space there and close that, you can see there, and I'll just move my beautiful face out of the way, that we've got all of these new modifications, and this was all sent over the network, which is pretty fucking cool. So if you, yeah, like as I mentioned in the intro, the big picture here, we're just doing like the Marvel Cinematic Universe of network programming, right? So stick around, we're gonna make this we're gonna make this even better. It's gonna be sweet. It's gonna be sweet. Cheers for tuning in.